My name is Thomas Thelen. I'm a graduate research assistant in the Department of Civil Engineering at NC State University. And today I will be presenting an application of 3DI coupled with an ocean scale hydrodynamic model to simulate multi-driver chronic coastal flooding. This work was developed with my advisor, Dr. Catherine Anardi, and the rest of the Sunny Day Flooding Project team. So as sea levels continue to rise, coastal flooding is happening more often worldwide, even in the absence of extreme storm events like hurricanes. In the GIF up on screen, a half-inch rain event that coincides with high tide causes flooding in Carolina Beach, North Carolina. While these chronic floods do not get as much attention as flooding from hurricanes, they do have real-world impacts. In this yellow box here, you can see garbage cans float away in the floodwaters and spill trash. And in this blue box here, a car stalls out and has to be towed out of the flood. So I'll let this GIF play through one more time here, in case anyone missed that. All right. Researchers have started to quantify some of these impacts to individuals, infrastructure, and businesses. For example, along the east coast of the US, there are 7,500 miles of roadway where your car might stall out, and 2 million people whose trash cans might float away. It's also important to note that these are present-day numbers. These floods will only become more frequent and intense with future sea level rise. Current methods for modeling and forecasting this coastal flooding, like bathtub modeling, do not consider the compound drivers that can contribute to flooding. However, multi-driver floods, like the rain at high tide example up on screen, do pose a hazard to coastal communities. A 2023 study by Gold et al. Found that 25% of floods in a coastal North Carolina town occurred during rain events. In this talk, I will present a coupled model framework that we are developing to simulate these hyperlocal, recurrent coastal floods from multiple drivers. I'm going to start by briefly overviewing the type of flooding that our group studies and the sensors that we use to collect data for model validation. Our group has developed a novel sensor to detect floods at roadway flooding hotspots by measuring water levels in storm drains. The Sunny Day Flooding Sensor, or SUDS for short, is a two-part sensor. A pressure logger in a storm drain, here, records water levels at infrastructure that's prone to flooding. A communication gateway with a camera mounted near the drain captures images to validate the spatial extent of water levels. SUDS capture flooding from the ocean, just like a tide gauge would. You can imagine this flooding overtopped the bulkhead here or came up through the stormwater system here. Either way, it is captured by the SUDS in the storm drain. But because SUDS are located within stormwater infrastructure instead of in the receiving body of water, they also capture flooding from land-based sources, like the rainfall example I have up on screen. SUDS are deployed in 3 partner communities in North Carolina. This presentation will focus on the town of Carolina Beach. This town is the focus of my PhD and the first location where we're developing a model to simulate flooding. We installed the first SUDS here back in February 2022. Floodwaters in Carolina Beach move from the harbor here to the roadway here, over land or via the stormwater system, when water bubbles up through storm drains and spills out onto the road. To simulate this flooding, I'm developing a coupled hydrodynamic and stormwater model of Carolina Beach. In the hydrodynamic model AXERC, we simulate ocean scale processes that drive local water levels, including tides, wind setup, and future sea levels. Our AXERC domain includes the entire Western Atlantic Basin here to fully represent tidal propagation and wind setup that can drive high water levels along the North Carolina coast here. In our model, tides are forced at the eastern ocean boundary, while atmospheric forcing, including wind and pressure, is applied over the entire mesh domain. In the much smaller 3DI model domain, we simulate localized flooding drivers like rainfall and runoff, infiltration, surface water flow, pipe flow, and local adaptation measures that the community might consider adopting, like raising shoreline elevations or adding wetlands. To couple the models, we take water level time series calculated by AdCirc at the water bodies around Carolina Beach, here, here, and here, and apply them as 2D boundary condition forcings in our 3DI model. With this approach, we have a one-way coupling from AdCirc to 3DI. I first developed the AdCirc simulations, calibrating the model against a water level gauge in the Carolina Beach Harbor. This is a water level time series from May 2022. On the y-axis are water level in feet. Sorry about that for y'all who are familiar with meters, but basically 3 feet is about 1 meter. In blue are water levels from a gauge in the Carolina Beach Harbor, and in orange are modeled water levels from AdCirc. From May 10th to 13th, water levels above the edge of road elevation, which is how our group defines flooding, result from an offshore low pressure system and winds that push water onshore. Here, the whole tidal cycle takes place at higher than normal water levels. On May 15th through 19th, we see flooding from a different driver. Water levels are above the road elevation due to king tides. Here we have higher than normal high water levels, but also lower than normal low water levels. We note that AdCirc accurately simulates peak water levels and timing with slightly better performance for tidally driven events. This is the same plot, but with water levels measured by a SUDS and a roadway storm drain in green, here. When the green storm drain water level line goes above the roadway elevation in red, we have flooding on the roadway. I want you all to note that the stormwater system distorts the tidal signal in the storm drain, such that peak water levels on the road lag peak water levels in the harbor. I also want you to notice the inflection points where we have a rapid increase of water levels in the storm drain. The town has installed duck bills, like the one pictured here, on stormwater outfalls that are supposed to keep water in the harbor from backflowing from the harbor into the stormwater system and out onto the roadway. SUDS data show that these valves are only partially effective in preventing flooding. They can hold back water temporarily, but at elevated water levels in the harbor, duck bills no longer prevent flooding. This may be because floodwaters can bypass duckbill valves by overtopping low-lying shorelines and moving overland to the road and stormwater system. Difference between water levels in the harbor and on the roadway is a motivation for using 3DI. The 1D, 2D simulations in 3DI are well suited for resolving the magnitude and timing of flooding that moves from an open water body through stormwater infrastructure or overland to upland areas and roadways. Because 3DI is a subgrid model that retains the bathymetries and topographies of the input elevation raster, this model allows us to resolve flood extents at the 1 meter resolution of our input digital elevation model. Up on screen, we have a drone image from another flooding event in November 2021 and modeled floodwater depths from the corresponding time step in 3DI. The drone image and the 3DI flood extents agree that water extends halfway up the box parking lot at this time step. In addition to looking at flood extent, we can also use a coupled AdCirc and 3DI model to assess the contributions of tides, rain, and atmospheric effects like wind to flooding water levels. The water level time series from a flood on January 22nd, 2023 shows measured and modeled water levels from a storm drain on Canal Drive, a flood-prone roadway in our study set. On the y-axis are water levels in meters this time, relative to the NAVD 88 data. The background shading shows measured rainfall intensity, and the dotted lines show water level measured by our storm drain sensor. The dash line shows coupled model results from the same storm drain for a simulation with forcing from all 3 flooding drivers: tides, atmospheric effects, and rain. When water levels go above the black roadway elevation line, there's flooding on the road. I want you to note that model results and measurements show similar flood magnitude and timing. We can extend this analysis to assess the individual contributions of our 3 drivers by running simulations with tides, rain, and atmospheric forcings turned on and off. The GIF up on screen shows the same January 22nd flood, but the coupled model simulation only includes tidal forcing. Atmospheric and rainfall forcings were not turned on in this run. I want you all to notice that while the boxed area at the top of this GIF is overtopped and flooded, the simulation results indicate that tides alone would not have caused flooding to reach our sensor on Canal Drive. But when we turn on atmospheric forcing in our flooding model, we see a different story. The contributions of tides plus atmospheric effects, namely wind, push water levels high enough that they move around the corner to our sensor on Canal Drive. The simulation with tides, atmospheric effects, and rain shows similar results, but with slightly deeper flood levels from the additional rainfall runoff. By hindcasting events with different combinations of flooding drivers activated, we can quantify the contributions of tides, wind, and rain to flooding at our study site. Now let's examine the time series from the January 22nd flood one more time. While the maximum flood depth and the falling leg of the flooding simulation results match water levels measured by our flooding sensor, there's a discrepancy here in the rising leg of flooding water levels. Measured water levels in the storm drain increase later than simulation results might indicate, because duckbills initially keep water from backflowing into the stormwater system. I'm currently developing control structures in 3DI to replicate the way duckbills moderate water levels in the stormwater network. The coupled model approach I have just talked through is a framework for simulating multi-driver coastal flooding at spatial and temporal scales appropriate for this hazard. The 3DI subgrid method resolves flood extents and depths at a resolution that captures flooding on the scale of city blocks. The ADCIRC portion of the coupled model simulates ocean-scale hydrodynamics that drive water level increases along the coast, while the 3DI portion captures localized flooding drivers and infrastructure impacts. Once we have a fully developed coupled model calibrated to data from our sensors, we will use this model to simulate future flood hazards by running simulations at different future baseline water levels as projected by sea level rise forecasts. We will also engage the community in a participatory modeling framework to see what adaptation pathways they might want to pursue and test the timescales and levels of future sea level rise at which these adaptation measures will effectively mitigate flooding. That's all I have for you all today. Thank you for your attention, and I would be happy to take any questions.
Okay, thank you, Thomas, and thank you also for your maintaining the time. A very nice presentation. I will try to see if there is any questions in the panel for you. I think there are none questions now, and in the chat there are also no questions. So I can proceed with one question in a parallel chat I have. Yeah, so Nikki here is asking about the coupling with that at the ADCIRC model. Is a one-way coupling. Do you think it will change your results significantly if it will be a full double coupling?
Yes, so that's a good question. The question was, would a two-way coupling significantly change between ADCIRC and 3DI significantly change our results? Our assumption is that it would not. The assumption is that the water inputs that we're adding in 3DI, which is namely rainfall, is minor compared to the water movements that we're simulating in ADCIRC. And part of the reason for that assumption is that it would be difficult to go back and forth between an ADCIRC simulation and a 3DI simulation and have them talk to each other and exchange water in real time. Though with the one-way coupling, we can run our ADCIRC simulation and then take our ADCIRC time series and input them into a 3DI simulation run. We don't have to have the models talk to each other. And so far, we found that one-way coupling seems to hold up in terms of 3DI water levels match ADCIRC water levels for the same location in the harbor. So it doesn't seem like developing a two-way coupling would be worth the additional simulation and setup time that it would cost. Did that answer your question?
Yes, I think so. Yes. Here at Masai. So actually, I have also a very similar question. Does these events you are analyzing, like they are, I mean, or maybe let me resentence. Have you analyzed what could be the influence of the wave height? Because basically with RCirc, you are not simulating wave height, and in the coupling, you're going usually with water levels. But then I was seeing your graphics and they are fit pretty well. So there is not like underestimation of the water levels, basically, that in other kind of storms could be because the wave are not simulating, basically. Can you have a small comment on that?
Sure. Can you all still see my screen here?
Yes, yes, yes.
Yes. So I think your question was about simulating waves in AdCirc, and it's a
Correct.
very good question. So the way that floods occur in Carolina Beach is the flooding doesn't come from the open ocean here. The the land is actually lower on the harbor side, so floodwaters move from the harbor, which is sheltered, to the roadway. And we've run AdCirc simulations, AdCirc and SWAN simulations, where we do include wave setup in our model, but we haven't noticed, or when we compared the harbor side water levels from our AdCirc simulation and our AdCirc and SWAN simulation, we found basically no difference. Just because it's a sheltered area, and although if there is wave setup, it's happening out here in the open ocean, and by the time those waves reach the harbor, they're basically negligible. The other important thing to consider here is a lot of this flooding happens during low wave conditions. We're not looking at hurricane type storms where we have large wave setups. We're looking at high tidal events or combined rainfall and tide events, or maybe an offshore low pressure system with some wind that results in a little bit of wind setup, but really not as much wave setup. So we found that waves aren't an important part of the chronic flooding here in Carolina Beach.
Okay, very nice. I have actually a second question. If no one else is having more questions, let me see. Yes, yeah, but my second, more than a question, is like an observation, because I found like very innovative. You are using these cameras to detect the floods, and also the pressure sensors to measure the water levels. And I wanted to ask you if you know about this open source Python package called Open River Cam, because once you have the cameras, you can install these Python packages. And basically, if you have a camera, then you can also calibrate to measure flow velocities. That later on is another parameter you can use to validate your model.